focus on cosmology. So that means that I study the universe, the contents of the universe, how everything revolves, how everything interacts, basically everything happening inside the universe. It's a great topic and I love talking about what I do. So for anybody following me on different platforms, I am now using Happs for all of my broadcasts. If you're still on Periscope, although I see a sign saying that Periscope is non-responsive. Okay, if you're watching me on Periscope, if you're watching me on Twitter, you want to start following me on Happs. This is where all of my future broadcasts are going to be. And if you follow me on Happs, if you use a link from me to get referred to Happs, or if I'm your first follow, the first person you follow on Happs, you might help me win a free mug this month. So, follow me on Happs, join me over on Happs, follow me on Happs, and then hopefully I might win a free mug. So this is actually the 8th week consecutively that I'm doing a broadcast. Hey, nice to see all the regulars. Hi, Rev. Hi, Angela. Hi, David. Nice to see you all. Welcome back. Welcome if you're a first-time viewer. Everybody is welcome here. So I used to do these broadcasts very, very regularly, like once a week. I used to do broadcasts where we talk about the universe, talk about cosmology. It was great fun. At some point, my broadcasting rate gradually decreased. I got to last year, 2020, everybody had a lot going on. But last year, I reached a point where I was only broadcasting once every couple of months. Now, around November or December, I thought, okay, I'm going to restart my broadcast properly. I'm going to go back to one broadcast a week. And then I saw the news that Periscope was closing down. So, you're requesting a song I absolutely cannot sing, and I will not sing unless it's like at a karaoke and I've had enough alcohol to forget that I cannot sing. So I cannot sing, definitely. You've requested a song. Thank you for the award. I appreciate it a lot, but I am not going to be singing today. Okay, so I saw the notification that Periscope was closing down. And then I heard of this new platform called Happs. And I was a bit reluctant to change, I don't like changing things. And then I watched a broadcast by my favorite neuroscientist, Ian McLaughlin. He's here on Happs. And I watched one of his broadcasts on Happs, and he was bringing up images on the screen and chatting to people. And I saw this and thought, okay, that's what I want in my broadcasts. So I came over to Happs. I tried out Happs once, absolutely fell in love with the platform. The broadcast studio is amazing. The community is brilliant. And when I joined Happs, there was a big notification saying, we're doing a Happs challenge, go live for 8 weeks consecutively to complete the challenge. So that gave me motivation. So now for the first time in probably over a year, I've been on doing a broadcast live for 8 weeks consecutively. Today will conclude my 8-week challenge. So to celebrate the 8-week challenge, or the conclusion of the 8-week Happs challenge, I want to tell you about 8 fun facts about the universe. Now, I see somebody saying, are you a boy or a girl? As you should probably be aware of, those are not the only possibilities. There are a lot of other possibilities there, and it is not relevant to the conversation, so I don't feel like I should answer that question. Okay, so the idea today is I'm going to talk about 8 facts about the universe that I find to be absolutely mind-blowing or amazing, or just, in general, very fun facts that I like discussing. So I'm going to start with the first fact, and as always, ask any questions. If I lose you, let me know. If you want clarification, let me know. If you have any interesting follow-up questions or comments, just let me know and we can answer all of your questions. Happs does seem to have some good features, feels a bit beta stage. It is in beta, Happs is still in beta, so that's why it feels a bit beta stage. But Happs has so much potential, and I really think Happs is going to become so great. I think Happs is going to do a lot of great things. So let's move into the first fact about the universe. And I'm starting with the fact that you might not consider to be a fun fact. So fact number 1 that we're going to discuss today, the universe could end at any point and without any prior warning. The universe could just stop existing. Fun fact. I'm sure you all agree that this is a very fun fact. So let's just go through what we're discussing here. So you might have heard me mention before about different ways the universe can end. In the future, we will either head towards a heat death, where the universe basically expands until nothing can interact, nothing can connect with each other. The universe ends up cold, empty, desolate. You might have also heard me talk about the Big Rip, where the universe would rip itself apart at its seams. And I realize I'm talking very quickly again today. I've slipped into my old Periscope habit of speaking quickly. So deep breath and let's go a bit slower. There's a lot to unpack today, so let's do it at a proper speed. So You might have heard me mention heat death, universe expands forever, no exchange of energy, no exchange of information, the universe ends up a cold, desolate, empty wasteland. Another way the universe might end in the future is heading towards a big rip. In the big rip scenario, the universe expands and carries on expanding, and this expansion becomes so strong that it can actually rip atoms apart at the seams. It can just tear atoms apart. Now, when this happens, when it tears atoms apart, the whole universe would basically disintegrate. Also a fun end for the universe. But there's another possibility that is not so distant into the future. Hey, David, thank you for the award. Very appreciated. Always happy to get awards. So there's another possibility for the end of the universe, which is more something that could happen at any time without any warning. And this is the vacuum decay of the universe, the vacuum decay of the universe. I notice I'm still not going live to Periscope. I don't know what's happened with the Periscope API, so hopefully my broadcast will still reach enough people. I do need a certain amount of viewers to actually complete the challenge, and I see the Periscope API is down, but hopefully it will come back up at some point. We have to see if that comes back. So, vacuum decay of the universe. It sounds fancy, it is, and let's discuss what vacuum decay means. So in order to discuss vacuum decay, there are two concepts we need to understand. Now, the first one is energy levels. Everything in the universe has an energy level. The higher the energy level, the higher the energy contained in a system. If you take, for an example, a piece of paper has a lot of potential energy because you can set it on fire and it will burn. Once you've burnt the piece of paper, you're left just with ashes, and the ashes will have less energy than the paper. The ashes are in a lower energetic level than the paper was because you've burnt it, you've gone to ashes. The second concept we need to think about now is stability. Now, everything in the universe wants to be stable. And by stable, you think if I have a link to Twitter, it goes to Periscope automatically. Yeah, I got a pop-up message saying Periscope connection unavailable. So yeah, apparently I can try toggling this. Let's see if I can try toggling Periscope from within the broadcast. Let's see if I can get my Periscope API working from here. Let's just try this again. Let's see what that does. There's so many nice features here. It's always a bit of twiddling and playing about with all the features. Yeah, Periscope connection still unavailable. Maybe Periscope has just disappeared 2 weeks earlier. Okay, so we've got the energy levels, where everything in the universe has its energy level, and we have the stability, where everything in the universe wants to be in its ground state. This means it wants to be at the state with the lowest possible energy. So for an example, imagine you have a hill or a mountain and you put a football at the top. This football is not really stable up there. At any point, it might roll down the hill to a new minimum, to the valleys. Everything wants to roll down and be in its minimum state, which also gives you a fun excuse if you're being lazy and don't want to do anything. You can just say you're staying in your ground state. It's not your fault. Everything in the universe wants to be in the ground state. So you just have to be in your ground state. It's not my fault I'm lazy. I'm just being in my ground state. Yeah, I am broadcasting to Twitter, so that should be enough. I was hoping to broadcast to Periscope as well. I'm bringing all of my regulars, but apparently Periscope is not working. Can't do much about that. Hey, Carrie, nice to see you. Thank you for dropping by, as always. So we have this idea. Everything has an energy level, and everything wants to be in the lowest possible energy. Everything wants to go down. Everything wants to be in its minimum. Thanks for the award there, Mike. Very appreciated. Always appreciate your awards. Thank you. Okay. So we have these two ideas. Everything in the universe is going to follow these principles of energy levels and aiming for the lowest energy possible. The universe is very lazy. Now, one thing about the universe is the universe gets its properties from quantum fields. Now, quantum fields sounds really technical, really weird, like what are quantum fields? And it is a weird concept. Quantum fields are things that permeate space-time. They're everywhere in the universe. And the easiest way to think about them is that quantum fields give us the rules for the universe. They tell everything in the universe how to behave, how to interact, how different particles should talk to other particles. All of this is encoded with quantum fields. So quantum fields really are like the rule book of the game of the universe. Everything in the universe is going to get its properties from these quantum fields. Now, quantum fields, like everything else in the universe, want to be in their lowest possible state, in their lowest energy level, which is actually called the vacuum state. And I should mention that this is a really bad name because this has nothing to do with the vacuum of space. This is just a vacuum state. It's just what we call it. Physicists are very bad at naming things. But when a quantum field or the rule book of the universe is in its lowest energetic state, we say it's in a vacuum. Now, there are many quantum fields in the universe that govern everything that we know about particle physics. And we think all of these quantum fields have reached a vacuum state, which means all of the quantum fields are stable. They're at the lowest energy level. They're not going to move. They're not going to do anything. They're just kind of there at their lowest point. However, there is one quantum field that might not be stable, and that is the Higgs field. Now, the Higgs field is the field that gives everything else mass. If you've eaten too much, you can blame the Higgs field. I just have mass because I interacted with the Higgs field. Is vacuum energy a real thing or just science fiction? Vacuum energy is a real thing. It also doesn't necessarily mean you're pulling out energy from the vacuum, but yeah, you can, once we're in these different vacuum states, you can have different energetic interactions, you can have vacuum energy. So the Higgs is the field that gives everything else mass. It's one of the most important fields in quantum mechanics. And the Higgs might actually be in a false vacuum. So let's go back to our idea that we have a hilltop, we put a football on top, this football wants to roll down. Imagine it rolls down and at some point stops. Now the football thinks, okay, I'm in the minimum level, I'm going to stop here, I've reached my ground state, I've reached the vacuum state in the case of the Higgs, let's stay here. But then you actually realize that's not the base of the mountain, that's just a place where the mountain flattened out slightly, and then the hill continues. So you went down the first part of the hill, you're in a metastable state, but it can still go down more. So this middle point here is called metastable because it's not a true minimum, it just pretends to be a minimum. So if the Higgs, I hope this is clear up till now, if it's not clear, let me know. Any questions, please let me know. If I've already lost you with the technical details, let me know and we'll discuss it again. We're still on fact one, we have plenty of time to get through the rest. Okay, so if the Higgs is in a false vacuum state or metastable state, at some point it might go to its real vacuum state, to its real ground state. Now, to do this, it could use, for an example, quantum tunneling, where it just gets over the last hill and then goes all the way down. Now, if this were to happen, the Higgs field has a lot of potential energy, so a lot of energy accumulated that's just waiting to be released. And as soon as it goes over that hill or tunnels through to that next vacuum, the Higgs field would plummet down to its true minimum, to its true vacuum state. When this happens, it would release a huge amount of energy, like a ridiculous amount of energy. This will create a new sphere with a new Higgs field and new physics. So in this new sphere, you will have, so inside a sphere, you can imagine inside this sphere, you have the Higgs at its new vacuum state. Now this is going to push outwards and pull everything down with it. It's like one part of the Higgs field has realized that it's gone down, and then it tells everything else, hey, there's another vacuum down here, we need to all go down. So this would propagate outwards from the initial vacuum decay at the speed of light. So you have this expanding ball of the new Higgs field going out throughout the universe. And anything that this ball touches, this expanding sphere, will be destroyed in a fraction of a second. If you come into contact with this field, life is destroyed. Atoms are ripped apart. The rule book is changing continuously. The rule book is changing throughout the universe. This means atoms are no longer bound together. Particles no longer have to interact the way they've been interacting up till now. It's like you suddenly rewrite the whole rules of the game. So everything that comes into contact with this expanding sphere will be eliminated from existence. Everything will just be deleted. If this vacuum sphere hits you, this expanding Higgs sphere hits you, you're wiped out. Within a fraction of a second, all of Earth would be gone. And this vacuum decay can happen at any time without any warning. It could already have happened because it's traveling at the speed of light. If the Higgs has already decayed a couple of billion light years away, it will take a couple of billion years to reach us, but it will reach us. Once the Higgs decay starts, the vacuum decay starts, there is no stopping it. There is no going back. We would have no warning. This essentially means that at any point, without any warning, We wouldn't be able to see it, we wouldn't see it coming, because it's traveling at the speed of light. So any information about this Higgs decay would reach us at the same time that it would reach us as well. We wouldn't see. Why will it propagate? So you can imagine part of the field as realizes a new minimum to go to a new ground state. And as it's going down, it's pulling everything else down with it. It's sending out the signal to every other part of the Higgs field saying, we have to go down. It's time to go down. We found our new minimum. This is where we're headed. So it will propagate at the speed of light, growing and growing and growing. And if you think this is like a bad scenario, everything this Higgs field touches or this expanding ball of vacuum decay touches would be completely erased from existence. It gets worse. It can actually get worse. This would replace the current universe with a new version of the universe where we don't know what the laws of physics are going to be like. It could be that in this new universe, life is not possible at all. So not only would we completely be erased, the whole universe might potentially never rebuild itself. So yeah, this is a fun fact about the universe that I decided to start on today. Now, the good news is that this is not expected to happen for at least 20 to 30 billion years. The Higgs seems to be pretty stable, hasn't happened yet. Our current best estimate is that if this happens, it will happen in about 20 to 30 billion light years. So we definitely won't be alive at the time. The sun will have already consumed the inner planets, Earth will be gone. So it's quite a few billion years into the future. If you consider that the universe is currently 13.8 billion years old, we would need to wait about 20, 30 billion years at least for this to happen. Assuming our calculations are correct, we might be wrong. This might already be happening. Then, of course, there's the other thing that if it happens really, really far away in the universe and the universe carries on expanding, maybe the universe expands fast enough that this Higgs decay would never reach us, and the expansion of the universe would save us from this Higgs decay. Maybe not. So if we're correct, this isn't something we need to worry about currently, but we can't know that for sure. The thing is, if this were to happen, we would not see it coming. We would have no warning. Just within a fraction of a second, everything we know would no longer exist. But we also wouldn't be around here to figure out that nothing in the universe exists. Apologies for the background noise. I have a very noisy neighbor living downstairs. Yeah, it's the end of the world as we know it, but we wouldn't see it coming. So, it's just something that might keep you up at night, but we don't really need to worry about it. It's completely out of our control, and there's no point worrying about things that we cannot control. So yeah, working from home problems, yeah. I mean, the kids are locked at home all day, so sometimes they're noisy in the hallway. It can be helped, completely understandable, and just have to put up with some background noise of the kids playing in the hallway. It's fine. So that was fun fact number 1. Let's see if there's any questions about the vacuum decay. Can we manipulate the Higgs field? We cannot. We can create more Higgses and the Large Hadron Collider. We can smash particles together and watch the Higgs come out. But managing quantum fields is kind of difficult because these tell us how the universe behaves. It's kind of difficult for us to tell these quantum fields how to behave themselves. There's a whole area of physics devoted to studying these fields, quantum field theory. It's actually a lecture I managed not to take, but is it theoretically possible to manipulate quantum fields? I don't think so, but I'm not completely sure on that answer. I'd have to check with people much more into the particle physics direction, but I don't think so. The quantum fields are kind of there and doing their own thing. Most we can do is produce reactions that will follow specific rules, but actually manipulating the Higgs field, I don't think we can do that. I saw the comment by Rev, why would the Higgs do this to us? I don't think the Higgs would do it intentionally. It just suddenly finds a new ground state. It's like, okay, I have to go there. Sorry, guys, I'm going down there to my new ground state. Nothing to be done about it. But yeah, I thought this was a fun fact to get started on today. Not all of my fun facts are going to be about the death and destruction of the universe or of the human race. Only 1 or 2 of them, maybe 3 of them. Most of them are going to be actual fun facts. Okay, so that took a lot longer than planned for the first fun fact. So let's move on to the second fun fact, and this is one that every time I hear, I have to think, wait, no, really? What? So, second fun fact. You should see on screen now. Supermassive black holes are less dense than water. I just want to leave that up so that can sink into everybody. Supermassive black holes are actually less dense than water. If there was a way to physically put a supermassive black hole on top of water without, the black hole absorbing everything, the supermassive black hole would actually float on water. And this is a ridiculous statement. Like, how can a supermassive black hole be less dense than water? We have the idea that black holes are the densest things in the universe. Black holes are regions where you have so much mass concentrated into such a small place that the gravitational force is so strong that nothing can escape, not even light. So you have a lot of mass in this region. We always say these are the densest objects or some of the densest things in the universe. But this is only true for stellar mass black holes. So black holes that are about the same size as our sun or a bit bigger, maybe 10 times the mass of the sun, 20 times the mass of the sun. But when you scale up to supermassive black holes, you get to less dense. And now I'm going to do something that I don't do very often in these broadcasts, and I'm going to bring up some maths. It's only 2 or 3 equations, and I'm going to walk you through it. Any questions, let me know. I know a lot of people don't like seeing the equations, but this is a big statement to make, that supermassive black holes are less dense than water. So I want to prove it to you. So I'm going to rely on just 3 basic formulas, or 3 formulas, to prove this to you. So I'm just bringing up the maths on screen. Now, again, any questions, just let me know, but let's go through it step by step. Now, the first formula you see in the top left here is the one that says RS is equal to 2gm over c squared. So this gives us the radius of a black hole. So to calculate the radius, you can calculate like how much mass do I need to put here to reach such a gravitational force that the speed of light cannot get out. Yeah, I've upped the level of my scopes, thanks. It's because I have Happs now, and Happs allows me to do all these cool features. There's also a screen share feature, and I have so many plans for science demos with the screen share feature. Okay, is density the same as weight in its capacity? Absolutely not. So we're not talking about mass, we're not talking about weight, we're talking purely about the amount of mass you have in a specific region. So the mass divided by the volume. Let's just ignore everything else on the screen and just focus in the top left corner. So this calculation here tells us how big, so the size of a black hole, if we know the mass. So the numbers you see here, the 2 is just a factor 2, it's a number 2. The g is the gravitational constant. Now the gravitational constant comes in because we're talking about balancing the gravitational force with the speed of light. Now m here is going to be the mass of our black hole. And you see this is divided by c squared. Now c squared is the speed of light in a vacuum. This comes in because we're thinking about the speed of, so we need the gravitational pull to keep everything down to the point that light cannot escape. So the gravitational constant is going to appear, the mass of the black hole is going to appear because it affects the gravitational pull, and the speed of light is going to appear. So the radius of a black hole is equal to 2 times this gravitational factor times the mass divided by the speed of light squared. Okay, hope that's clear for now. This is a formula you can pull out from general relativity. If you've never seen the formulas of general relativity before, you can now say you've seen the formula for at least one thing in general relativity. Now, the second formula on the right-hand side is about the volume. Now, black holes are spheres. So if we want to calculate the volume of a sphere, we know how to do this. We know how to calculate the volume of a football. The volume of a sphere is going to be 4/3 times pi times the radius to the power of 3. When something's to the power of 3, it means you multiply radius times radius times radius. So now let's focus again. At the beginning, we had radius is equal to mass plus, like, times some numbers. Let's just ignore these numbers because they're constant. The gravitational constant is constant, the speed of light is constant. So my volume is going to be proportional to the mass cubed because it's proportional to the radius cubed, and the radius is directly proportional to the mass. Any questions, just let me know. I know a lot of people don't like math, and I can understand if you haven't seen it before, if you're not used to math, it's always difficult. So I'm just walking you through this quite slowly. But any questions, just let me know. So now we can go to the actual definition of density. What is density? And density is the amount of mass you put in a place divided by the volume that you're putting it in. So the mass contained in the volume. So you have mass divided by volume. Now we saw before that the volume, changes like mass to the power of 3. So if I just ignore all of the numbers, again, I'm dropping the 4, I'm dropping the 3, the pi, the g, the c, all of these are just numbers that are not going to change. So I can just move them aside. So my density is going to change like mass over volume. Volume goes like mass to the power of 3, which means my density is going to change like the mass divided by mass cubed. You can cross off one mass at the top, one mass at the bottom, and at the end you reach the conclusion that the density of a black hole will change like 1 divided by the mass squared. So at the end of the day, the density changes like mass, so 1 over mass squared. This means that if the mass increases, the density decreases. If you increase the mass of a black hole by a factor 10, its density will decrease by a factor 100. So I hope that makes sense. If not, please do let me know. Does the physics of it mean they have to be spherical, or can they be different shape? Great question. Very, very nice question. Now, let me just get rid of the formulas here. So because of the way the gravitational force is pulling everything inwards, we generally think that black holes have to be spherical. There have been some exceptions, but in the same way that stars are spherical and planets are mostly spherical, because you have kind of equal gravitational force everywhere, such a big object as a black hole, is very much expected to be spherical. And there is the joke that physicists just think of everything as a sphere because it's easier to compute. You know, if you want to know anything about a cow, you need a spherical cow in a vacuum. So I know the formulas might be a bit off-putting to some people, but with these formulas, you can pull out the idea that the density of a black hole is inversely proportional to its mass. The more mass, the less density, which means when you scale up to supermassive black holes, which are a million times the mass of the sun, your density is going to go straight down. So once your black hole has a mass of about 10 to the 37 kilograms, so this is a 1 followed by 37 zeros. This is also 10 million times the mass of the sun. Once your black hole reaches this mass, your black hole will be less dense than water. Above masses of 10 million solar masses, your black holes will be less dense than water, which means hypothetically, if you put them in a body of water, they would float. What would actually happen is the black hole would suck up the body of water and the planet around it, but they have less density than water. So the biggest black hole that we know, the biggest black hole we've been able to see in the universe or observe, is 60 billion times the mass of the sun, which means its density is 0.0045 kilograms per cubic meter. Now, for comparison, the density of air in our atmosphere, where we are, is about 1 kilogram per cubic meter. This means that the biggest black hole we have been able to find has less than 1% the density of air, which is absolutely ridiculous. And anytime I hear this fact, it's like, wait, what? No, that can't be right. No, but it is. We've seen the math. This is how it works. Supermassive black holes can be less dense than water. They can also be less dense than air. Great fun. If black holes spin, do they bulge at the equator? Very good question. I don't think so. So it's a very valid question, because if things spin, you often think they might bulge at the equator. Earth does, so Earth is slightly flatter at the poles because of its spin. Now, black holes, I think the gravitational force is so great that even if it's spinning, it will still maintain its spherical shape. Now, there are some that deviate, but overall, even if they're spinning quite quickly, they should still be able to maintain their spherical shape. Is the Schwarzschild solution still the only usable solution we have? There's another type, so a bit technical here, when we describe a black hole, we use general relativity. A black hole is one possible solution to the description of general relativity that we have. There are others, such as a Kerr black hole. Now, a Kerr black hole is one that is spinning. A Schwarzschild black hole is not spinning. A Kerr black hole is spinning. I think I always mix those up, but that should be the correct answer. So there are other solutions, but not many. There are not many solutions to Einstein's equations just yet. Okay, so I'm going to speed up a bit because I've done 2 facts in 30 minutes. I was supposed to do 8 facts in 45. So I'm going to move on to fact number 3. As always, if you have any questions, please do let me know. I'm just going to once again try to connect my Periscope because that's where most of my followers are. And I need to get my followers in here to reach the number count I need. Okay, So let's bring up fun fact number 3. That is not number 3. I cannot count. Aha. Let's bring up the one that's actually called number 3. You just got a sneak preview of number 6. Okay, number 3. We just talked about supermassive black holes, how they might even float in water, fun things like that. And now the even more fun thing. There are a lot more black holes in the universe than we realize. There are a lot of black holes in our galaxy. There are many, many more black holes than we would think of. So when we think of black holes, we think of these stars that have reached the end of their lifetime, they've collapsed, they formed a star. Sometimes black holes merge together, form even bigger black holes. Sometimes you get a lot of black holes coming together, you form supermassive black holes. We think, we're not completely sure how supermassive black holes form. But it's always, a lot of people have this idea that black holes are these scary objects in the universe that suck up everything around them. You know, there's no escaping a black hole. Black holes are there. Nothing is going to escape a black hole. But black holes are actually not so bad. Black holes are very common in our universe, and black holes are only dangerous if you get close enough. So if you're far away from a black hole, you don't need to worry about the black hole. You only need to worry about a black hole if you get very close. And the reason is that the black holes work via the gravitational force, which is actually a very, very weak force. The further away you are from an object, the less you feel the gravitational pull. If you're able to go far enough, there could be hundreds of black holes around, and you don't need to worry about it. So one question that comes up often is, how do we see black holes? So black holes are these objects that are so massive that nothing can escape, not even light. So how do you see it? If a black hole is not emitting light, if a black hole cannot physically send you a signal, how do you see it? And we can see black holes by its presence on other objects. We'd have to stop the broadcast, go to settings, disconnect, and reconnect it. I tried clicking on settings and reconnecting Periscope twice. It still did not connect, so I'm not sure. I keep getting the message that we've attempted to connect this broadcast 5 separate times. The Periscope API is non-responsive. So, my account settings, okay. Yeah, I think I can keep the broadcast going. Thanks, Pablo, for stopping in and giving the advice there. I don't want to disconnect the broadcast and restart. Let's just keep going, and hopefully at some point, people will come in anyway. But thanks, Pablo. Thanks a lot for coming in and offering advice. I really appreciate it. I love Happs. You get technical support if there's an issue in the broadcast. It's just so nice. Okay, so how do we see black holes? We see black holes with their influence on other objects within the solar system or within the galaxy. For an example, if a black hole passes through a cloud of hydrogen, it might suck up this hydrogen. This hydrogen might start accelerating, might get heated, and it might produce X-rays, which is light that we can see. Does dark matter fall into black holes? Excellent question. Yes, it does. Black holes will pull in anything because it uses the gravitational force. Dark matter is an object with mass. It feels the gravitational pull of a black hole. Dark matter will equally fall into black holes in the same way that normal matter does. The difference is when dark matter falls into black holes, it's not going to create these lights that we see. It's like a accretion disk of matter falling into the black hole because it's not going to emit light. But when normal matter goes into a black hole, it can emit light because of the way it's accelerated, because of the way it goes in. Another way we can actually see black holes is if a star gets close enough to a black hole, it can actually be ripped apart. You can actually see stars being eaten up by the black hole. It gradually gets torn apart and gradually gets sucked into it. Can anything be eaten by black hole without causing energy? I don't think so. And so there's always this exchange of, it's a big question, like what happens to the energy of a particle that falls into a black hole? One idea would be that the black hole uses this energy to kind of grow. It adds to its own mass. So technically, any process where the object falls into a black hole will have a specific energy associated to it. It's not always energy we can see, but it will have some exchange of energy. Are there dark matter black holes? There could be. The cool thing is we don't know what black holes are made of. We cannot know what black holes are made of because we have no information on what happens inside a black hole. Nothing can escape a black hole once it's got close enough. So whatever is on the inside of a black hole, we have no way of knowing it. We can't actually go in and see what's in there. Hey, Michelle, nice to see you. Thanks for stopping by. So yeah, there could be dark matter black holes, but we really don't know what black holes are made of. So yeah, it could be anything. Space is so fascinating and so terrifying. Pablo, I hope you heard my first fun fact, because that was the most terrifying one. And I will get to another fun and fascinating and terrifying fact close to the end as well. Put my terrifying fact at the start and at the end. So just to give you some numbers on black holes, these objects that could suck us up, spaghettify us, spit out, not even spit out our bodies, should keep us suspended in orbits. How many black holes are there within the Milky Way? So based on these things, where we can look at how stars move, we can look at the energy coming from particles accelerated around black holes, we currently estimate that there are between 10 million to 1 billion black holes in our galaxy. This is not in the universe, this is in our galaxy. This means that for every 1,000 stars in our galaxy, there is a black hole. So there is a ridiculous amount of black holes in the galaxy, like a ridiculous amount of them. And the good thing is, most of them won't do anything to us. Most of them are just minding their own business. We're minding our own business. And we do really think of black holes as being really bad. So I want to tell you that black holes are not so bad, and I'm going to prove it with two numbers, which might make you even more scared of black holes. The nearest black hole to us, the closest one that we've been able to see to Earth, is 11 times the mass of the Sun, so it's quite a small black hole, and it is 3,000 light years away. So it's still close, but it would still take 3,000 years traveling at the speed of light to reach this black hole. So this black hole close to us, it's 3,000 light years away. It's not so close, it's also not so far. For comparison, the supermassive black hole at the center of the Milky Way, every galaxy has a supermassive black hole at the center. These are the ones that are lighter than water. The supermassive black hole at the center of our galaxy is 25,000 light years away. It's also 4 million times the mass of the Sun. It's pretty big. So black holes sound like these nasty objects that are going to kill us, but they're less likely to kill us than, for example, the Higgs field, which could just decay and eliminate life on Earth, as long as you don't get close to a black hole. If you get close to a black hole, it could wipe you out. Then there's the fun fact. I like doing the fun, scary facts here. There are some black holes that are not really tied to any specific object, and they're just hurtling through the universe in random directions. And those could be a problem if they come close towards us. These are known as rogue black holes. Yeah, there could be some rogue black holes. So on the topic of rogue black holes, I'm going to move into my fourth fact of the day. There are rogue planets and rogue stars which are traveling alone in the universe without being gravitationally bound to any object. Okay, so let's get into what I mean here. Now, anytime we think of a star, we tend to think of, okay, stars are within the galaxy, they're gravitationally bound. Our star is the center of the solar system. It's within the Milky Way. We're moving around the center of the Milky Way. We're in one of the Milky Way's arms. We're kind of happy here. But there are a lot of stars that are not bound to the galaxy. They can move about freely. Just to give you an idea of how difficult it is to get this, in order for a star to be moving without being gravitationally bound, or even to escape the Milky Way, there are stars that can escape the Milky Way, you need to give them a pretty big kick. You need these stars to be moving really quickly. So just for comparison, when we launch something into orbit from Earth, what we're trying to do is we're trying to beat the gravitational pull of the Earth. To do that, we need to reach what is known as escape velocity. Now, the escape velocity on Earth is 11 kilometers a second. If you can launch a spaceship at 11 kilometers per second, you're going to get it to go up into orbit also. So in order to get a star to leave the galaxy, to kick a star out of the galaxy, you need to reach the escape velocity that overcomes the gravitational pull of all of our galaxy. And the gravitational pull of all of the galaxy, in order to counter this, the escape velocity is 500 kilometers per second. And now these stars are objects that are 10 to the 30 kilograms in mass. That's 1 followed by 30 zeros. That's how many kilograms of mass is in a star. And that's a small star. So how can you possibly accelerate a star to travel at 500 kilometers a second? How can we do this? There are actually 3 ways we can do this. First one is with supernova. So when a star reaches the end of its lifetime, it will run out of things to burn, it will create heavier elements, it runs out of fuel, and then a star is a constant pull of gravity pulling things inwards and pressure pushing things outwards. Once you have nothing to burn, the pressure stops, you only have gravity pulling things inwards, the star collapses, then you've got so much material in such a small region that it explodes outwards as a supernova. This also distributes all of the heavier elements throughout the universe. But if you have 2 stars, there are a lot of stars that are in binary systems, so you have 2 stars moving around each other. If one of these stars goes supernova, it pushes out enough energy that the other star can be thrown out of the galaxy. So one star goes supernova, its companion can be thrown out of the galaxy, traveling at about 1,200 kilometers per second, which is ridiculous. Rogue black holes are worried again. Why have they gone rogue? Do they disagree with black hole politics? Yeah, they're kind of just doing their own thing. So on what I'm saying here, if you have a rogue star, so a star that's traveling freely throughout the universe, and this star collapses as a supernova, does a supernova and leaves behind a black hole, you suddenly have a black hole remnant. It's like the black hole, the star watches one of its partners in the binary system explode and kick it out of the universe, and it does the same. Not out of the universe, sorry, out of the galaxy. Out of the galaxy. You cannot kick anything outside of the universe. I hope I didn't say that many times there. You're kicking the stars outside of the galaxy, they're traveling faster than 500 kilometers per second, and they're going to do their own thing. Black holes can do the same. If you have a supernova close to a black hole, you could also kick this black hole out of the galaxy. Another way, so supernovas is way 1 to kick stars out of galaxies. Way number 2 to do this is to fly the star. Obviously, you can't fly the star yourself. If the star goes close to a supermassive black hole, rather than being sucked in, it might do the slingshot maneuver. You might remember this from Armageddon, the movie that has the most scientific errors of any film ever. But it does have this nice slingshot maneuver where you go close to something and you use that to fling yourself around. If a star gets close to a supermassive black hole, rather than being eaten up, it can actually sling itself around and be shot out of the galaxy. Fun thing to do. But actually, the most common way for stars to end up as rogue stars traveling throughout the galaxy, throughout the universe without being in a galaxy, is actually when galaxies collide. So a lot of galaxies are heading on collision courses. We're going to collide with Andromeda, the closest galaxy to us. When this collision happens, there's so much gravitational distortion that it kind of disrupts the orbit of all of the galaxy. So about half of the rogue stars that we've been able to see, we think became rogue stars when the galaxies merged and spat out these stars. Galaxies collide, there's so much things happening, the gravitational fields overlap, the stars get kicked out. The question now is, how common are these stars? They did the slingshot in the novel version of 2001. Yeah, they also did it in Roadrunner and Coyote. They do this slingshot maneuver so frequently, it's a good thing to do. Okay, I see a nice question by Revolution there. Could rogue planets have life on them if they have a hot core? That is an absolutely excellent question, and I will get to that in 2 minutes. So the question is, of all of the stars that we know, how many are currently or could be rogue stars? And the estimates are that about half of all of the stars in the universe could be rogue stars. So rogue stars are actually pretty common. And now it leads us to the second point here, of rogue planets. So rogue stars are stars that are not trapped within a galaxy and they're traveling around the universe doing their own thing. Rogue planets are similar. They're planets that are traveling throughout the galaxy, but they're not trapped to a specific star. They're no longer gravitationally bound to their star. They've just been kicked out. They have no light to warm them. The surface is going to freeze. The atmosphere is going to freeze. And they're just gradually traveling throughout the galaxy and sometimes even in between galaxies as these cold frozen blobs or chunks of rock. There are 3 different ways, or 3 main ways, that planets can become rogue planets. Planets can be kicked out of their star system. Got new glasses and I'm still not used to them and everything is still slightly dizzy here. Okay, so in a young star system, when a star is just formed and all of the protoplanets around it are kind of fighting for dominance, they're trying to clear up their orbit, they're trying to become real fully fledged planets. At this point, there's a lot of collisions happening. Things haven't settled down yet. Rocks are smashing into each other. And this can actually be fast enough to kick, or a strong enough collision to kick a planet out of orbit. If a star is kicked out like that, could it keep its planets? It could. It depends. Depends on how it's kicked out. Depends on the speed at which it's kicked out. But because the planets are more controlled by the gravitational force of the star, if the star is kicked out, the planets would probably follow. Maybe not all of them, but they probably would follow, which is good. You can actually live around a rogue star. As for on a rogue planet, we'll get to that. That's also a very good question. So, another way that you can have a planet being kicked out of orbit is in this early phase where you have a lot of rocks coming together. If one of them gets too close to the sun, again, we could have this slingshot maneuver and it could be kicked out. But now the best way you can actually get planets to go on their own journey is if a planet is disrupted by a rogue star or a rogue black hole. If you had a rogue black hole suddenly come through the Milky Way, come through the solar system, which can happen, Earth might be kicked out, it might be disrupted, it might be sent out from the Milky Way, from the solar system, it might be sent out from the solar system, which is not fun. The current estimate is that within the Milky Way alone, there are billions of these rogue planets, and up to half of the planets that we know of could eventually become rogue planets. So like half of the planets in the solar system could actually become rogue planets at some point. So what happens when a planet becomes a rogue planet? As it gradually moves further and further away from its star, the planet is going to cool down. Any water on the surface is going to freeze over. The atmosphere is also going to freeze over. You're going to have a couple of kilometers of frozen ice on the top of the planet. Now, any planet, like the Earth, for an example, 99.7% of the energy on Earth is the energy we get from the sun. But there is this other 0.3%, which we get from actual movement within the Earth itself. So at the center of the Earth, there's this solid lump of rock, of metal. Then there's melted metal around it and rocks, and all of this is in constant movement. It's gradually slowing down and cooling slightly, it's solidifying. This releases a huge amount of geothermal energy. It releases all of this geothermal energy. If a body is loose in space, how can it lose its temperature? Through what medium? It's not so much that it's losing its temperature, it's that there's nothing there to maintain the temperature. So in the case of these planets, for example, 99.7% of their energy comes from the sun. When the sun gradually moves around, they have no energy to prevent the vacuum of space from cooling everything down. But geothermal energy could keep the core warm enough that it could actually lead to the point where you have a layer of liquid water underneath the kilometers of ice. So underneath these kilometers of the frozen atmosphere and the frozen lakes, you could still have liquid water kept alive by geothermal energy. Could anything live down there? When we're talking about kilometers under the ice, completely dark, no light, could anything live there? And actually, if we base ourselves on what we've seen on Earth, the answer is maybe. If we take the Mariana Trench, 11 kilometers underneath the sea, no sunlight reaches down there, but we have been able to find down there geothermal vents, so hot air coming up from underneath the Earth's core, hot material coming up from underneath the Earth's core, not underneath the core, underneath the Earth's surface. And this is providing enough heat that we have actually been able to find life forms around the Mariana Trench. And these are life forms that 50 years ago we did not think was possible to exist. So the question we've asked just now is, could a rogue planet have life on them? If they have a hot core, they absolutely could. If you have enough geothermal energy, you could actually sustain life in these underground water regions underneath kilometers and kilometers of ice until the geothermal energy runs out, which is a couple of billions of years. Now, this would be life entirely different to any life we're accustomed to. There wouldn't be any light down there, it would be underwater, but bacteria could survive. And this is one of the reasons, not so much because of rogue planets, but if we think about moons within our solar system, you might have heard of the moons of Jupiter, like Europa and Enceladus. All of these core moons, and Enceladus is Saturn. You have all of these core moons, and some of these are completely frozen. They're like solid blocks of ice. But there's the hope that underneath the layers of ice, there might be bacterial life. We haven't checked yet, but we're trying. but we still haven't completely ruled out the possibility of finding life within our solar system. Now, we wouldn't be talking about little green men or little red men, little Martians. We'd be talking about bacteria, but it would prove that life could exist in these atmospheres, in these surrounding areas. So, cool fun fact there. You can have rogue planets, you can have rogue stars, you can have rogue black holes. The universe is ridiculous in the fact that you could even have life on one of these rogue planets, which is, again, absolutely amazing. I hope you all agree that these are super fun facts. I love these fun facts. Okay, moving on to fun fact number 5. Fun fact number 5, there are no green stars. Now, you might think this is obvious, you've never seen a green star. So the question is, why have we never seen a green star? We see plenty of stars around us. As stars get hotter and hotter, they move from going red so stars look red, then they look orange, they look yellow, they look white, they look blue. So we've seen blue stars, we've seen white stars, yellow stars, orange stars, red stars. We have never seen a green star. And this is a big question of why not, because if we look at the electromagnetic spectrum, green is kind of in the middle. If you go from blue to red, you kind of have to pass through green. So it's a very valid question of why have we not seen green stars? And the answer is that green stars actually cannot exist. It's not just that we haven't seen them yet, it's that green stars cannot actually exist. So the reason green stars cannot exist, all stars are behaving like black body radiation. This means that stars emit all frequencies of light. They will emit equal amounts of blue, green, red, ultraviolet, infrared, but depending slightly on their temperature. The hotter the star is, the peak of this black body spectrum will shift either to one end or to another. Now here's a cool thing. Our eyes it will depend on the temperature. Depending on the temperature, we shift to one side or to another. But we can cover all possible temperatures in between, but we cannot cover all possible colors in between ultraviolet and infrared. And the reason is that our eyes can only have 3 color receptors. Our eyes see red, blue, green. Any color we see is a combination of red, blue, green. Now, any color that your mind imagines is different amounts of red, blue, and green. So now I'm going to bring up a very cool image. I did not make this simulation myself. I hope you can all see the credits in the top left corner because the person who made this deserves the credit for this. So here you can see a shifting spectrum of what a star would like as the black body shifts depending on the temperature. On the one hand, we have ultraviolet stars, which are the hottest stars. They emit a lot of light in the ultraviolet region, which we don't see. They emit a lot of blue light, not much green, not much red. So we see them as blue stars. On the other side, in the infrared region, we're going to emit a lot of these are the coldest stars. They're going to emit a lot of infrared light. They're also going to emit a lot of red light, but they're not going to emit much blue or green light. So we will see them as red. But when this peaks at the center of the visible spectrum, this is when we have kind of medium temperature stars, we produce equal amount, or the star is going to produce equal amounts of blue, red, and green photons, particles of light. Our eyes are going to put all of these together and see white light. So what you can see here is how much red, blue, and green there is in each time in these nice circles moving at the top, and the overlap between them gives us the color of the stars. So when you have very, very hot stars, you're going to have blue stars. When you have very, very cold stars, you're going to have red stars. When you have normal temperature stars, you have all possible wavelengths, they overlap, and the result is that you see white light. Yeah, this is pretty cool. Green stars would also be invisible in front of green screens. They would be, if you had a green star in front of a green screen, how would you know? Well, you would know because it would be emitting heat and energy. But yeah, you could use a green star as a green screen. But unfortunately, green stars don't exist, and there's this cool animation made by Ben C. Bartlett. You can find him on Twitter. He did this animation, and it's amazing. So we can actually prove why there are no green stars. And I love that fact. That's just so cool. I love that there are no green stars and that we can actually specifically explain why there are no green stars. Okay, now I'm going to go on to the fun fact that I accidentally clicked on before, and I will click on it properly now. And now we're moving away from stars and things like that into a slightly different direction. In the vacuum of space, you can fuse or weld metal together without needing any heat. Now, this doesn't sound right. This sounds weird, right? On Earth, if you want to weld metal together, if you want to weld metal together, you need to heat it up. Normally, you heat it up to the point where it reaches its melting point, it goes slightly liquid, you put it together, then it solidifies. We've seen this process on Earth many times, we know how this happens. But if you actually do this in space, if you have two perfectly clean blocks of the same metal and you put them together, just a very small amount of pressure, you just put them together, they will actually weld together into one piece of metal. Without any heat, just in cold welding together system, in the vacuum of space, these two very, very clean identical metals will weld together. If you think what I'm saying here is crazy, don't take my word for it. Look at the evidence. I'm going to show you a video of two pieces of metal in a vacuum, and you can see when they come in close contact, they melt together. So these are two pieces of exactly the same metal, perfectly clean in a vacuum. Initially, there are two pieces in a gear moving, and at some point, they just become one piece of metal, which could be a problem. This is not a simulation. This is something we have actually been able to see. So the question is, why does this happen? How do two pieces of metal suddenly become one piece of metal? Right? It's just like, whoa, you see that and think, wow, how does that happen? Now, any metal is a combination of positively charged ions, so these are atoms without their electrons that are positive, and these form a grid. And around this, you have electrons, which are negatively charged, which are moving freely. So the atoms or the electrons within your block of metal are always moving freely. This is how metals can actually conduct electricity or conduct heat. You can move these around. It seems almost immediately, it is, right? It's just so fast. You put these metals together and they're one metal. It's amazing. Now, in space or in a vacuum, if you have perfectly clean metals of exactly the same type, when you put them together, the atoms don't know that they're different blocks of metal. They have no way of knowing. It's like, I'm moving freely in this piece of metal, I'm moving freely in this piece of metal. We put them together. The atoms don't know that they're different pieces of metal, and they will fuse together. And this is ridiculously mind-blowing. So the question is, why don't we have this problem on Earth? Only metals or crystals do? Only metals. In crystals, you don't have so many atoms moving freely. So like if you have a diamond, for an example, it's a very rigid structure. You don't have atoms moving freely. But in metals, the properties of metals is that you have these atoms kind of moving around. So on Earth, we don't have this problem because anytime you have a metal, there is a thin layer of oxygen around it, or a lot of oxygen around it. This will create a very, very thin layer of rust or of oxide. So when you put their metals together, there is a separation. They know, okay, I can't go past here because there's something in my way. There's a bit of rust, there's a bit of oxygen, there's a bit of oxide. This is also why we need very, very clean blocks of metal. If your metal is not clean, then this will not happen. If you put lubricant on your metals before you put them in a vacuum, they will not be able to do this. But if you can actually be in the circumstance of a perfectly clean metal of exactly the same type in a vacuum, so no air, they will melt together. It's still amazing. Now, can they use this for repairs outside of the International Space Station? They could, but they tend not to, because this is actually a very bad thing. It's something that you can't really control. You're going to put two pieces of metal together, they're stuck. You're not getting them apart. They're now one piece of metal. One way that we actually discovered this, or one problem we had with this, in 1991, there was a spacecraft, Galileo, that was heading to Jupiter. It was going to take some photos, some images, send them back. Had two antennas, the low-gain antenna, which is normally just used for basic communication, and the high-gain antenna, which is for the big pictures. What happened is when they got to Jupiter, they tried to open their high-gain antenna, and it had welded itself in place. This was not supposed to happen. Usually with spacecrafts or with missions like this, they put a lot of lubricant and coating on top of their metals to specifically avoid things like this. This spacecraft had several delays. It was sat in storage for about 5 years, and by the time it was launched, they didn't recheck this. And in the end, the high-gain antenna was welded shut and could not be deployed. In fact, they had to use a low-gain antenna for all of the science. The ways to avoid it is to either use different metals, slightly different alloys, slightly different compositions, different lubricants, or use plastic. And this is something that is now accounted for anytime you build a spacecraft. And while this is like ridiculously cool and amazing that we have to be aware of this in space, it also has a lot of cool applications. This type of cold welding is now being used in nanotechnology. So in nanotechnology, you often want to fuse together these tiny, tiny components, and any type of heat might damage them. Hello from St. Petersburg. I've never been there. I want to go there at some point. Oh, hello from Cologne. So in nanotechnology, sometimes using heat is a problem because you can melt things, you can damage it, but you can actually use cold welding. So it's something cool that we discovered in space accidentally that now has applications for nanotechnology. And I just want to show it one more time because I will not get over how cool this video is. Two metals, same metal, two different pieces, put them together, they immediately meld into one piece. Absolutely amazing. I love this. This is a thing. Okay, 2 facts to go. I'm 1 hour in. I was planning on going for 45 minutes, but I promised 8 facts, so we're going to get through the 8 facts. Okay, time for fact number 7. And now I'm moving back to the destructive power of the universe and giving everybody nightmares and thinking about fun ways the universe can kill us all. And now I'm going to talk about powerful exploding stars, known as producing a gamma ray burst. And a gamma ray burst is something that could cause a mass extinction event and could wipe out all of life on Earth, or at least most of life on Earth. Also, very fun thing to think about, of course. So, what are gamma ray bursts? What do we need to do about them? What do we need to worry about? Now, just imagine if you could take all of the stars that you see in the night sky, all of the stars within 100 million light years around you, and focus this into one beam of energy. You'd have created a super weapon. And the universe has already done this. The universe has created the super weapon. So within the electromagnetic spectrum is the different energies that light can use. We're used to very different frequencies, right? But if you go down to very small energies, you have radio waves, you have microwaves, then you have infrared, where we can kind of see things, ultraviolet, X-rays, moving up to the higher energy. And once you reach the highest energy, right, the highest energy, you're at gamma rays. So gamma rays are the highest energetic particles of light, the particles of light with the most energy we've ever been able to see. I will get to the magnetosphere and the ozone and why it doesn't actually help us in this case. So gamma rays. If you take one photon that contains a gamma ray frequency, or one photon of gamma ray frequency, this is more energetic than 1 million visible photons combined. So if you take 1 million visible photons, particles of light that you can see, they contain less energy than one particle of light at the gamma ray frequency. These are ridiculously energetic processes, ridiculously energetic photons, really, really high energy. And they're so energetic that they can break apart atomic bonds. They can rip electrons out of atoms. They can dismantle the structure of DNA. It won't turn you into the Hulk, unfortunately. It will just dramatically alter any form of life, which makes them very dangerous. But we're lucky. We have a layer of ozone around our planet which protects us from these gamma rays. We have our atmosphere, we have ozone, we did a lot of the damage to it. It's gradually repairing itself. And the ozone is protecting us from these gamma rays, from these really high energy bursts of light that occur within the universe. So the ozone protects us. Now, 50 years ago, at some point, we sent up a spacecraft. It was actually a spy satellite looking for anything happening. It was a US spacecraft looking for anything happening in Russia during the Cold War. And instead of finding anything from missiles or stuff like that, this satellite actually found gamma rays in the universe, gamma ray bursts. These are faint bursts of light that last only a few seconds. Now, the first one we were able to locate, the first gamma ray burst we were able to say is coming from up there, came from a galaxy that is 6 billion light years away. 6 billion light years is a very, very long distance, which means in order for us to see this gamma ray burst, this burst of light that lasted a few seconds, that was produced 6 billion light years away, this energy burst had to pack more energy in those 1 or 2 seconds than the sun will emit in its entire lifetime. This means that gamma ray bursts are the most energetic objects in the universe. They are the brightest objects in the universe. So where do gamma ray bursts come from? What can produce such high energies? What can produce these bursts of electromagnetic radiation at such high frequencies, such high energies, sorry? And there are two types of gamma ray bursts that we've been able to see, the long gamma ray bursts and the short gamma ray bursts. Now, the short gamma ray burst lasts for about a second. You have to go set up an entomology survey. Oh, that sounds so fun. Squishy biology is great fun. I love squishy biology. Thanks for joining. I will look out for your entomology broadcast. That also sounds very fun. I hope you do entomology broadcasts. So, long gamma ray bursts, short gamma ray bursts. The short gamma ray bursts last about a second, and they are produced when you have two neutron stars. These are super dense stars. These are actually super dense stars, spiraling around each other until the point where they crash. When they crash, they emit a huge beam of light, a huge amount of energy. This produces a gamma ray burst that lasts about a second. Or you can have a long gamma ray burst. A long gamma ray burst lasts about a minute, and it's produced when you have a supernova. So a supernova is a star that's exploding. We've already discussed supernova a bit today. So you have a star that's reaching the end of its lifetime, it collapses, it explodes as a supernova, it leaves behind a black hole. So both in the merging neutron star and in the black hole production, what you're left behind with is a black hole. Now this black hole has a magnetic field around it. This magnetic field also has a disk of gas around it, so you have the magnetic field, the disk of gas. Now, because of the huge amount of energy and the spin that goes into both these supernovas and the merging neutron stars, you can actually wind up the magnetic field. So the magnetic field ends up kind of pointing in this type of shape. Imagine you have the supermassive black hole here at the center, the black hole here at the center. The magnetic lines are going to converge and go out like this, which creates two funnels. Funnels pointing up and down, they can be in any direction, but opposite ends of your black hole, you're going to have these really high energy funnels caused by the bending magnetic field. Any particle that goes in there is going to be shot out at great speeds. So now we have a production mechanism. Neutron stars, black holes being created, they bend their magnetic field, it creates this funnel. Throughout this funnel, high energy particles can move. Okay, and because of the way these magnetic fields are, the particles released, or the particles that are shot towards things, will stay very focused. It's a very focused beam. It's kind of the difference between shining a normal flashlight on something, you see the light disperses, and shining a laser beam, where you see that the light stays focused. Now, because of the production mechanism of gamma rays in this tightly wound funnel, the gamma ray burst stays focused, which means it's extremely high energy concentrated in a very small region. And there are hundreds of these gamma ray bursts. We detect on average one every day. So every day we see one of these gamma ray bursts, these huge flashes of energy in the universe that last a few seconds and that you can see. Most of them are harmless so far. So far, we've only been able to see ones outside of the Milky Way, which are probably too far away to hurt us. But what would happen if we had a gamma ray burst within our galaxy? Not only within our galaxy, but pointed towards us. So we have this kind of funnel, we have the jet of high energy gamma rays. What would happen if this was pointed directly to Earth? If this gamma ray burst takes place only a few light years away from us, so really close, this is not a quasar, it's similar. So a quasar is the same process, but on larger scales, where you're talking about a whole galaxy. And now I'm talking about just one star producing this gamma ray burst. One supernova, black hole combination producing this gamma ray burst. If it's within a few light years, it would ignite our atmosphere. It would literally set the planet on fire. It would burn the planet. If it's within a few light years, like 5, 10 light years away, this gamma ray burst would be so high energy that it would ignite our atmosphere, which is kind of a problem. We don't want our atmosphere to be on fire. If it's within a few thousand light years on the other way, it gets even more fun. But imagine it's like 8,000 light years away, or 4,000 light years away, kind of pointed towards us. It could sweep through the solar system like a tidal wave. And it would completely destroy life as we know it on Earth. So there will be three processes here. We mentioned before the ozone protects us. Now, the ozone is used to protecting us against small gamma rays coming from the sun. It is not used to protecting us against this gamma ray burst, this high energy gamma ray burst coming towards us from such a star, our ozone layer would be completely depleted. Within a second, our ozone is gone. If the ozone layer is gone, it means we're exposed to all of the ultraviolet light from the sun, which will gradually heat up the Earth over the period of a few years because the ozone takes a long time to replenish itself. If we wipe out the whole ozone layer in a fraction of a second, or in a second, there is nothing protecting us from the sun's radiation, which means that the Earth could become completely devoid of life because the sun would burn everything on the planet. Another thing that could happen with this gamma ray burst pointed directly towards us, depleted ozone, let's say, while we're waiting for the sun to heat up the planet and burn us, you're going to have nitrogen oxide, which is going to cause a chemical smog around the planet. This chemical smog is actually going to block out the light of the sun, which could lead to a freezing event. It could block photosynthesis. It could also have catastrophic effects on life. Why is the beam directional? Because of the way the magnetic field bends around the black holes that you've created, it creates a funnel, a high energy funnel. So all particles traveling around the black hole are accelerated by these magnetic fields until they reach the point where they can escape via the funnel. So then it's very directional. And the third effect of this gamma ray burst hitting the Earth head on is that it would elevate the nitrogen dioxide levels in the atmosphere, which would produce acid rain. Nitric acid is toxic to pretty much every living being. So the ozone layer gets depleted, the planet gradually heats up and starts burning. We're completely exposed to ultraviolet radiation, which is damaging for our DNA. Of course, the gamma ray burst has already damaged our DNA. We have nitric acid falling down from the sky. We have acid rain. We have smog covering parts of the sky where we can't see the sun. This could be a mass extinction event. This would wipe out many, many species. It could be life ending on Earth. And this might already have happened. In fact, there was a mass extinction event 450 million years ago where 85% of the species in the water were completely eradicated. There are some hints, based on some evidence we've been able to find, some hints that this could have been a gamma ray burst event. Could have been something else as well. We cannot know for sure, but it might already have happened. There's also the idea that these gamma ray bursts might actually be, so there are living beings that can survive nitrogen oxide, not many. It would be a total biological reset. So some might survive, some probably, maybe the ones at the bottom of the ocean might survive, but yeah, nitrogen oxide is pretty damaging for almost everybody. You suddenly prefer the event at the beginning where we have the vacuum decay. Yeah, the event I mentioned at the start where the whole universe just blinks out of existence is kind of preferable to this. So we think that these gamma ray bursts could actually be one of the reasons that we haven't found life outside in the universe. It could be that if a lot of galaxies have these gamma ray bursts, it could render most galaxies completely inhospitable. If you have 10 of these gamma ray bursts happening every year, at some point one is going to hit you. There could have been mass extinction events on planetary scales across the cosmos caused by gamma ray bursts. Our current estimates is that because of these gamma ray bursts, probably only about 10% of the galaxies we see can actually host life for long periods of time, which makes life on Earth even more amazing. So, how likely is this to actually happen? Do we need to worry about gamma ray bursts wiping out life on Earth? Now, based on the age of the Milky Way, we think, and the structure of the Milky Way, we think that these events might be about one gamma ray burst every 10,000 years or every million years. So in 1 million years, you might have one gamma ray burst in the Milky Way, and it's only dangerous if it's close by and if it's pointed at us. However, if it is close by and pointed at us, again, we would have no warning. The first thing we would know about this gamma ray burst is when it's about to wipe out life on Earth. There would be nothing we could do about it. If a gamma ray burst has already gone up pointing towards us, there's nothing we can do about it. So, no need to worry about what we can control. Now, the good thing is that based on the galaxies where we've seen this happening and based on our galaxy, we don't think that it's so likely in our galaxy. It doesn't seem to be the type of galaxy that has a lot of gamma ray bursts. So it's probably not going to happen. But there's a lot of if statements there. What's the beam width of these bursts? So if one gamma ray burst happens about 4,000 light years away, the width of the beam by the time it reaches you would be about 100 light years wide. So it would really, there's no escaping it. If it's heading towards you, there's no escaping it. So can this happen in our galaxy? Probably not, but there is one nice star called Ultraviolet 104, which is 8,000 light years away. It's a star that's at the end of its lifetime. It's currently burning helium. We're very sure that this star is going to go supernova. We're not sure if this star is going to produce a gamma ray. So there's several questions. If this star produces a gamma ray, if this star is pointed towards us when it produces this gamma ray, and if it actually is slightly closer than what we think, this star, 8,000 light years away, could actually trigger a mass extinction event on Earth when it goes supernova, which is expected to happen in the next million years. So this could happen, but there's a lot of ifs here. It's not very likely. You might have heard me say before, there are thousands of ways the universe can kill us, and the universe comes equipped with these big sniper stars that are just waiting to wipe out entire civilizations. But it seems like we're lucky enough to be in a galaxy where we probably don't need to worry about gamma ray bursts. We think, we hope we don't need to worry about gamma ray bursts. We're not completely sure. So suddenly the vacuum decay will at least we blink out of existence without feeling anything. Seems a lot better. So I know I've done two very scary facts here. 1 million years, so we have some time. We do have some time. There's nothing we can do about it. If that star decides to go supernova, there's nothing we can do about it. We have at least 8,000 years to develop some kind of shielding. If this star is going to go supernova, we wouldn't know until it hits us. So it's 8,000 light years away, right? So it takes 8,000 years for the light to reach us. But as we're seeing it currently is how it looked 8,000 years ago. It could already have gone supernova, and there could already be a gamma ray burst heading towards us as we speak. We don't know. We hope not. We think not. So I know I painted some very bleak facts about the universe. There are thousands of ways the universe can kill us. This is something we know. I covered two. There are many more. There's a great book by Katie Mack called The End of Everything, and it speaks about all of the fun ways the universe can kill you. The two I mentioned are just ones that I think are really cool that the universe can actually do this. I hope they don't happen. Hello from Branson. Hello, Jay. Nice to see you. Thank you for dropping by. So I want to end on my 8th fact, 1 hour and 20 minutes into what was supposed to be a 45-minute broadcast. I'm really bad at timing these broadcasts. I want to end on a fact that makes me feel better about the universe, that makes everything seem actually better than these bleak ways the universe can kill us. And the last fun fact I want to discuss is how some of the atoms in your body are over 13 billion years old. The atoms in your body are eternal. Some of them have been around for 13 billion years. So we're all used to the phrase by now of, you're made of stardust. We are made of stardust. A lot of our atoms were formed in supernovas, in stars, and events that spread out these different atoms throughout the universe. But all of the hydrogen in the universe was formed just after the Big Bang. A few minutes after the Big Bang, hydrogen formed. You could actually form the basic atom, the simplest atom. Every hydrogen atom in the universe was formed at the Big Bang. And we contain, or just after the Big Bang, and we contain hydrogen. In fact, let me just show you how much of our body is actually hydrogen. I have a pretty picture here where you can see the composition of the average human. We are about 65% oxygen, 10% carbon, 10% hydrogen, a couple of percent nitrogen, and others, which includes calcium. So the carbon in your body, the oxygen in your body, this was produced in a star. The star exploded and allowed humanity to take place. We would not be here without the carbon. All forms of life that we know have a lot of carbon and oxygen. These are the building blocks of life, and these were formed in stars. But the 10% here that you see of hydrogen, which is in every human body, this was formed in the Big Bang. just after the Big Bang, in the early universe, when all of these particles came together, when structure, not even structures, when the first atoms began to form, the hydrogen was formed. So the hydrogen that is in your body today, that is in water, that is in so many things, water is H2O, the H there is hydrogen. All of this was created in the Big Bang. So not only are we stardust, we are also cosmic dust from the beginning of time itself. Thank you for thanks, Isa. Always appreciate the awards. And if anybody here doesn't follow Isa Betancourt, you should. Amazing bug scopes. If everything you ever wanted to know or didn't want to know about bugs, go follow Isa. So there are parts of you, parts of every human that have been formed in the early universe. Parts of me are 13 billion years old. I find this so incredibly reassuring because my atoms have been around a long time. My atoms will be around for a long time. It's kind of like my turn to use the cosmic atoms. When I die, my atoms will go back to the universe and move on to the next thing. I just painted these amazing ways the universe can kill us. But the universe will not get rid of our atoms. Okay, the Higgs decay will. But these atoms were formed 13 billion years ago. They've withheld a lot, and they're here helping us be alive. I want to share another image here, which I also really, really like, and I'm actually going to put it in hero mode, of the origin of every atom on the periodic table. And it's a bit small, so I'll just color-code it. You see the things in pink, for an example, are formed by fusion, where you have cosmic rays fusing together. The things in green are formed by exploding massive stars. The things in yellow are formed by dying massive stars. So the carbon, the nitrogen in your body is formed by a dying star. The oxygen in your body is formed by exploding stars. But the hydrogen, the one in the top left, the hydrogen in your body and everything around us was made exclusively in the Big Bang. So all of the hydrogen in our body comes from the Big Bang. What's cosmic ray fission? Yeah, I should have looked that up before flashing this picture. Honestly, I don't know. Based on the name, I assume it's cosmic rays in the universe that have very high energy that can crash together high enough to produce these higher elements, but I did not check that before showing this image, and I should have done. But yeah, it's just another way of creating a few elements in the universe. And yeah, I did not look, I should check everything before showing images. But I find this fact just really, really nice. Of all the fun facts today, this is the one I wanted to end on because the universe is vast and crazy and ridiculous, and there's so much happening in the universe. The universe also has a way of persevering. This is not the image that is supposed to be left up, by the way. This is supposed to be back on me by now. So the atoms in us, some of our atoms come from stars, some of them come from exploding stars or dying stars. But at least 10% of me, all of the hydrogen in me, was produced in the Big Bang. It's going to stay here with me until I'm done with it, and then I give it back to the universe. Yeah, I find this absolutely amazing. This is the fact I wanted to close on. I've talked about ways the universe is going to kill us. Amazing things in the universe with metals welding together. There are no green stars in the universe. Black holes are really abundant. Black holes can be lighter than water, or less dense than water, sorry. We can have rogue planets. We can have rogue stars. We can have gamma ray bursts that are going to wipe out humanity. We can have the Higgs decay, which is going to wipe out all of life. But at the end of the day, we're all part of the universe, and it's never more present than when you think about where our atoms came from. I want to leave you on that philosophical thought. I see I'm actually a few viewers away from hitting my 250 target, which would have ended my Happs challenge. It's a shame that this didn't go out to Periscope. Oh, it just jumped up to 249. Okay, almost there, almost at the threshold. But in any case, I will be back online on Sunday doing another broadcast. Sunday will be back to my weekly broadcast of, ask me anything about the universe, generic chat, come with all your questions. So I will be back online on Sunday, probably for an hour, probably at 6 p.m. No, not 6 p.m. Sorry, 5:30 Central European Time. So that's in GMT +1. I will put out the announcement on Happs beforehand. So even if I didn't, I'm not sure yet if I have reached the 250 yet or not. If not, it doesn't really matter. I will do a broadcast again on Sunday. So I wanted this to be like concluding the 8 weeks, but if not, I will conclude it on Sunday. It's fine. We just got a nice fun broadcast with 8 fun facts. More math, please. Yeah, I'd be happy to do more math. This is a general question. How do people feel about the math? Was it too much? Did I lose you with the math? If people like the math, I can bring it back. I can do more. I'm happy to show you more equations, but I'm always worried that if I show too many equations, I might lose some people. So thanks, Isa. I'm waiting to see if you can bring somebody on. So math is great, awesome. I can try to throw in some more equations, especially now that I have, this cool thing that I can bring stuff up on my screen. I can share my screen. I can actually now show equations much, much easier. So I will try to do more equations, but I also don't want to lose people. So I will try to find a balance of some equations, but without losing people. Can I do Noether's theorem? Noether's theorem. Wow, Noether's theorem is one of the prettiest and most elegant theorems, or not theorems, yeah, theorems in the universe. Yay, thank you, Isa, thank you, Georgia. You've put me over the 250 views. Awesome, this should now have completed my Happs challenge. Absolutely awesome. Looking forward to scopes in Finland and hearing Finnish words. Yeah, when I move to Finland next year, I will absolutely do scopes in Finland. Broadcasts in Finland. Maybe when I'm out walking around in nature, I will try to do broadcasts. I'm sure there's amazing things to see in Finland. Thanks, Isa. I really appreciate you bringing in the missing one. It's now at 258. So thank you, everybody, for making that happen. Happs challenge is done. 8 fun facts about the universe. And at some point, we'll add in more maths. So yeah, I am moving to Finland. I will be moving to Finland at the end of September. In October, I start my new job in Finland. So yeah, big months coming up. Get to move country again. It's going to be fun. I'm not sure about learning Finnish. It seems so complicated. But yeah, it's going to be fun. Okay, thank you everybody for tuning in. This has been a great fun broadcast. I really enjoyed it. Definitely longer than expected. I hope you all had fun. And remember, we're all part of the universe. So I hope to see you again soon. And I hope that in the meantime, you stay safe and take care of each other.